Hi everyone! So one of the most powerful uses of mass spectrometry is to be able to determine the identity of an unknown. At least as a starting point, being able to determine the formula for a compound gets you a long way towards that goal. So that's what we're going to talk about here, although we're not going to really show you exactly how mass spectrometry is used to identify unknowns. We're going to save that for another video. But today I'm going to talk to you about how the mass accuracy, or how close you get to the real mass, really goes a long way to distinguishing the differences. So I'm going to give you some definitions here just to illustrate some of the pitfalls that we deal with when it comes to mass spectrometry. And the first definition is what we call an isotopomer. So what is that? Well, basically we're talking about a compound that has the same chemical formula, but the atoms are arranged in a different way. So let me give you an example here. So here you have the active ingredient in the drug Zantac. And you see that this comes in two different forms, the cis and the trans. Now, in fact, we're not really talking about isotopomers here. These are just cis and trans. So the compounds are really arranged with the same connectivity to them. But what I want to get at is this. Notice the chemical formula. If you were to identify a compound that had that formula, does that mean that you have one of these two forms? Not by a long shot, because if you just took that formula and let's say entered it into a program here, and ChemSpider is one example database that you could use. So let's just say that we've identified that the formula for unknown is what I showed you on the previous slide. We could enter that into ChemSpider and take a look. And you see that it's in the thousands. The amount of arrangements of those particular atoms into different molecules really could go on forever. So not to say that every one of these is a true compound, but still, the point is if we just have the molecular formula, we don't necessarily have the identification of our molecule. Now that's okay. Determining the formula actually does go a long way to identifying an unknown. And there are other techniques that we can use to look at the connectivity of the atoms. So let's just say that we're only going to go as far as determining a formula. That's good enough for now. Now let's look at another definition here, and this one is called an isobar. So I gave you the definition before of a nominal mass, where you just kind of round things off to a nearest integer. So if you were to ask the question, how many different formulas can you come up with on a mass of 28 on the nominal scale? I mean, there's not that many. N2CO, C2H4, what else would there be? I mean, sure, you could say H28, but that's not a molecule, right? So looking at reasonable combinations, I'd say this is what you got. Now let's take a look at this mass spectrum over here. As far as I can tell, there really is no difference, no matter what these compounds are.
I can't see the difference. Can you see the difference? No, I can't see the difference. Can you see the difference?
Price is the difference.
I grew up in a different time than you. It's one of those things that's stuck in my head. So what am I talking about here? Well, depending on the mass spectrometer that you use, you actually might be able to get a difference. So let's just look at that same compound on a better mass spectrometer, one that provides more mass accuracy. And you actually see that these compounds do have differences between them. The differences are extremely subtle, but you notice that some things are ahead of 28 and some things are a little bit lighter. Let's just blow this up. So what we see here is that two of the three peaks have masses that are above the nominal mass, so we just say that they have a mass sufficiency. And likewise, we have one of these peaks that's below the mass of 28, so it has a mass defect. These definitions of mass sufficiency and deficiency come straight from the fact that atoms, you'll see that some of them are higher than their nominal mass and some of them are lower. And just to highlight them here, you actually notice that it's the low mass compounds that have the mass defect. All the bigger atoms down on the bottom, they have a mass sufficiency. This really goes back to the E equals mc squared argument. The bigger the atom is, the more energy it takes to hold it all together. But anyways, this is a term that you can use, or a piece of information that you can use to help you to identify compounds. I'll just leave that topic for now. So back to the spectrum at hand. What I'm really drawing here would be like the theoretical mass spectrum. We have three hypothetical masses that just seem to appear on the scale somewheres over here. Now, what if I'm to actually record a mass spectrum? Where would it lie? Well, let's just say that it lands right here. Have we identified our compound? Well, you can see that the arrow, the mass measurement that we've done, is close to one of the peaks. So I guess that means that we've probably identified it as the peak in the middle. And that one corresponds to that, right? But hold on. What if we were to repeat the measurement? So the next time we measure, we get that. And actually it just sort of spreads all over the place. So using this particular mass spectrometer, we haven't really hit the target. Our masses are spread out all over the place. And to put numbers on that, we're actually seeing the mass distribution spreads out by about 0.2%. So this is extremely low mass accuracy. With an instrument that's that variable, we're never going to be able to distinguish one compound from the other. So let's say now I've sort of traded up. I'm using a mass spectrometer that has much higher mass accuracy, and this time we get this measurement, but the next time we measure it and the next time, it all lands down to the same spot. If you were to have an instrument that has that degree of mass accuracy, I think you could confidently say that you must have pinpointed onto this particular unknown. Likewise, if we take another measurement with a new unknown and all of our data happens to cluster over there, I think we're pretty sure now that we've identified the other compound in the mix. The question that I have for you here is, what is the minimum level of mass accuracy that it would take to distinguish all of these molecules? And I guess the question comes down to, well, where is the closest point? I mean, it seems pretty easy to distinguish the one way off the end there, but it's the two that are close to each other. That's what we're interested in. Especially if our measurement happens to lie kind of right in between the two, like which one of these two peaks is that corresponding to? Well, at least if we said it's sort of clustered to one side more than the other side, then I think we'd have a better chance of it. So what we need to do is measure the gap between those two peaks, and we'll be able to distinguish it. So the masses that we have here give us the gap between the two. And what you actually need to do with that measurement is divide it by 2. Now the halfway point is simply like the point halfway between these 2 points. You have to be at least to this side or that side of that minimum. So that's why we're dividing that gap by 2. So the number that we get here turns out to be about 200 ppm. Now that's not very high mass accuracy, but then again, this is a pretty small molecule. So we really don't need that much to be able to identify it. Now I'm just curious if anybody's picked up on this, but of that mass 28, yeah, H28 is not a reasonable molecule, but there is another reasonable molecule that we could put down that I think you could draw a nice structure for. There is a compound that has a mass of 28. I'm just curious if you might be able to figure out what that is, maybe from the mass that I'm reporting here. So if I was giving you the question of saying, give me all the possible structures that have a mass of, 44, well, you could sit down with pen and paper and you could come up with a reasonable list. It might take a while, especially when you're not really sure what the limitations are. Okay, maybe I'll say it only has carbon, hydrogen, nitrogen, oxygen. Now you can only come up with a limited number of combinations. But what if I were to extend that mass? What if I said, write down all the possibilities with a mass of 100? Now that's getting a little bit insane, right? You'd be there like forever. So fortunately, there is another way around this, and that's using our friend ChemCalc here. So in ChemCalc here, we're going to go to this second tab, and what we can do here is enter a mass. So that would be like a theoretical mass that we've observed in a mass spectrum, and it's going to calculate and print out like all the different possibilities, all the elements that we can make to get to that combination. What we need to do is specify the mass accuracy. 500 ppm is the default, and we're also specifying which elements we can use. So for example, if I'm going to throw in sulfur as a possibility, the list is going to go up. If I were to increase the mass range, so instead of 100, I'll go to 200, then logically there's even more combinations that can come up to a mass of 200. It doesn't even fit on the first page. There's 4 different pages here, so it is actually 200 to work out. Now if I increase this to 500, strangely enough, it still shows me only 200 on the list. So I'm pretty sure that ChemCalc is only displaying the top 200 that have masses closest to the number that you're entering. That should be more than enough to figure things out. The elements that we're using here, they could go on. So for example, there could be chlorines or fluorines or phosphorus or sodium. These types of questions of like which elements do we have, they may or may not be available to us. You may be able to learn something from the mass spectrum or some other external information that would give us a hint as to which elements are present. We'll be talking about that in another video. So I just wanted to show you this tool here, which you can use to determine possibilities for your formulas. This alone doesn't necessarily tell you the identification of your unknown compounds based on mass, but that's exactly where we're going to be going in the next video. So we'll see you around next time.